All right, welcome to the deep dive. You know how this works. You send us the research, the articles, those messy notes you scribble down. We basically turn it all into the good stuff, the insights that'll make you sound like you spent weeks on this stuff. Today, we are diving deep, way deep into this thing called double machine learning, DML.
Yeah, double machine learning, DML. You sent over this paper, really interesting paper on DML and how it's kind of changing how we figure out, well, how do we know if one thing actually causes another?
Yeah, and the paper had some really cool examples, like does getting more education actually lead to people earning more money later on?
Or in medicine, right? Like, is there a real link, like a cause and effect link between smoking and, unfortunately, lung cancer and things like that?
Right, or even something, if you're in marketing, right, and you change the price of something, how do you know if that price change is really what made people buy more or less of your product? Yeah, cause and effect. It's like
Yeah.
everywhere, right? But the tough part is a lot of times we can't do a perfect experiment. We got to work with the data we've got, the real world stuff.
Right, we call that observational data. Like we're just observing what's happening out there. And that's where things get tricky. There's all this stuff happening in the background, all these other factors that could be messing with our understanding of what's really causing what. We call that confounding. It's like trying to figure out if a plant grew because of the fertilizer or because it was sitting by the window getting more sunlight.
Totally. And to figure those things out, the usual way, like the way we've always done it,
Yeah.
sometimes makes some pretty big assumptions, especially about how all these other factors are connected to what we're looking at.
Yeah, and those assumptions, especially when you're looking at really complicated stuff, those assumptions can feel kind of shaky.
Exactly, yeah.
Yeah.
So that brings us to what DML is trying to do. It's trying to use all the power of machine learning, all those algorithms that are so good at finding these hidden patterns, but in a very clever way.
Yeah, it's not just about making predictions, which machine learning is great at. It's about like using machine learning to like loosen up those strict assumptions that we usually make and getting closer to like the real cause and effect, even when it's like super messy and complicated.
So today we're going to unpack all of that, what DML is, why it's so cool, and what to watch out for if you're thinking of using it yourself. We're even going to look at how DML is being used to study things like how much air pollution affects housing prices.
Yeah.
Okay, so first things first, what exactly is DML?
So at its heart, DML is not about just taking some fancy machine learning algorithm, running it on your data and saying, boom, this is the causal effect. It's more nuanced than that. It's about strategically using machine learning as a key part of like a really well-established statistical framework that's like specifically built for figuring out cause and effect. One very common and powerful framework where DML really shines is something called the partially linear regression model.
Yes.
We call it PLR.
PLR. Um, for those of us who didn't spend all our time studying statistics, what are the key pieces of that? What do we need to know?
So imagine you have something you're trying to understand, some outcome, we'll call it Y, and then you have this other thing, the thing you think might be causing Y, and we'll call that the treatment, or W. Now, of course, there's usually a whole bunch of other factors, right? Things that could be influencing both W and Y, making it really hard to tease apart what's really going on. These are our confounders, which we often label as XC.
Right. It's like all those pesky hidden variables that might be messing with our results. We've got to account for those.
Exactly. And the tricky part is that we often don't know the exact relationship between those confounders, XC, and both our treatment, W, and our outcome, Y. These relationships could be super complex, not just a straight line, but all curvy and unpredictable.
So we're not talking about simple stuff here. We're talking about the real world where tons of things are interacting in ways we don't fully understand.
And that's where DML really shines. It lets us use machine learning to embrace that complexity without having to perfectly guess the exact form of those relationships. It's like letting the data guide us toward a more accurate understanding, even when things are messy and nonlinear.
So how does DML actually do this? What are the tricks up its sleeve?
There are two main techniques. The first one is called orthogonalization, and it's closely tied to this idea of double robustness. Essentially, DML estimates models for both the outcome and the treatment separately. And this is super important because it makes the final estimate of the causal effect way more resistant to small errors in either of those models. Think of it like building in a safety net.
Okay, so it's almost like a checks and balances system. If one model is a bit off, the other one can kind of help compensate?
Exactly. It's like having two slightly imperfect tools, but by using them together in a smart way, you can get a much more accurate measurement than if you relied on just one. It's all about reducing the impact of those small, inevitable errors we make along the way.
That's really clever. What's the second trick DML uses?
The second one is called cross-fitting, and it's all about being really clever with how we use our data. We split the data into, say, k different folds, and then for each fold, we train our machine learning models, one to predict the treatment, one to predict the outcome, using the data from all the other folds.
Okay, so we're basically training our models on most of the data, and then like testing them out on a fresh batch they haven't seen before.
Exactly. And for that fresh batch, we calculate what we call residuals, the difference between the actual values and what our model predicted. We do this for both the treatment and the outcome, and then we run a simple linear regression. But instead of regressing the outcome on the treatment directly, we regress the outcome residual on the treatment residual. This gives us a coefficient, and we do this whole dance, holding out a different fold each time. In the end, we average all those coefficients, and that's our final estimate of the causal effect. This whole cross-fitting business is all about preventing something called overfitting, which is where our model gets a little too cozy with the training data and doesn't generalize well to new data.
And you know what? The paper actually lays all this out in algorithm one, which actually made it a lot easier to follow.
Yes, algorithm one. So just to recap, the steps are split the data, train the models, predict on the held out data, calculate those residuals, run the regression, repeat for each fold, and then average those coefficients. And there's even an optional eighth step.
Oh, right. Step 8, which is super smart. You repeat this whole process like a bunch of times, maybe like S times each time with a different random split of the data. And then you take the median of all those final coefficient estimates. This just makes the whole thing extra robust, especially when you're working with smaller data sets.
Exactly. So we're using machine learning to deal with all that complex confounding, but we're doing it in a way that's like extra careful and rigorous, using orthogonalization and cross-fitting to make sure our estimates are as reliable as possible.
All right. Now, it's important to point out what DML can't do. Like, it's amazing at dealing with all those assumptions about the shape of the confounding, and if the ML method is doing variable selection, might even help us figure out which variables matter most. But it doesn't solve the fundamental problem of, what do they call it, unconfoundedness. So even if DML handles those observed factors perfectly, if there's something big we missed, something we didn't measure, we're still in trouble, right? It's kind of like you could polish a turd, but it's still, you know.
Right. Garbage in, garbage out, as they say. If there are factors influencing both the treatment and the outcome that we haven't measured that aren't in our data set, DML can't magically account for them.
No amount of fancy statistics can fix that. So are there like other pitfalls we should be aware of?
Yeah, definitely. One that trips people up sometimes is this idea of bad controls. These are variables that you might think are helpful to include, but actually they introduce more bias instead of reducing it. One classic example is a collider, which is a variable that's caused by both the treatment and the outcome. Imagine we're trying to understand if playing a musical instrument as a kid makes you more likely to be successful later in life.
Right, so playing music is the treatment and success is the outcome.
Exactly. Now imagine we control for something like going to a fancy music school, which could be caused both by having musical talent as a kid and by coming from a wealthy family, which might also influence your chances of success. If we control for that, we might actually create a fake negative relationship between playing music and success, even if there wasn't one originally. DML, on its own, doesn't know which variables are good or bad controls. That still requires a deep understanding of the cause and effect relationships at play.
So we can't just throw every variable we have into DML and hope for the best. We need to think carefully about what we include. Okay, so DML gives us this really cool framework, but what kind of machine learning algorithms can we actually use within it?
So the paper talks about a bunch of different algorithms. There's the classic linear regression, often combined with something called lasso, which helps with automatically selecting which variables are important. But then you've got all these more flexible methods like generalized additive models or GAMs, random forests, boosted trees, one popular one is XGBoost, and even neural networks, which are like the super fancy ones.
That's a lot of options. How do we choose? Like, what are the main differences between all these?
Well, they differ in their flexibility. Some, like random forests, boosted trees, and neural networks, are amazing at capturing those curvy, nonlinear relationships in the data. Linear regression and lasso, in their basic form, are, Well, linear. You can tweak them to be more flexible, but it can get complicated fast.
Right, right. And what about figuring out which variables are the most important? Like, does DML do that for us automatically?
Some methods do. Lasso is really good at that. It basically shrinks the influence of less important variables down to zero. And tree-based methods like random forests and boosted trees, they also kind of do this implicitly as they're building those trees. Linear regression, GAMs, and basic neural networks, they don't do that on their own. You'd have to add something extra.
And I bet those more complex methods, like the ones that can handle all those crazy nonlinear relationships, they probably need a ton of data to work well, right?
That's right. Flexibility comes at a price. They can learn all sorts of intricate patterns, but if you don't have enough data, they might end up memorizing the data you do have instead of learning general principles that apply to new data.
The paper also had some thoughts on which ML methods might be especially good for using with DML, right?
Yeah, they were a bit cautious about using Lasso by itself, especially if you think there might be a lot of nonlinear stuff going on. They found that it could lead to biased estimates in those cases. And they were really impressed with gradient boosting, specifically XGBoost. It seemed to do well in all sorts of different situations, so they recommend that as a good starting point.
So XGBoost, got it.
Yeah.
They also said something interesting about how accurate those machine learning models are at predicting the treatment and the outcome in that first stage of DML.
Right, that's a key insight. Basically, the better your chosen ML method does at predicting the treatment and the outcome from those confounders, the more confident you can be in the final causal effect estimate it spits out. Of course, this assumes you've taken care of those bad controls and potential unobserved confounders.
Got it. So picking the right ML method for your data is super important. Now, the paper also did a bunch of testing, both with simulated data and a real-world example. What did they learn from those simulations?
So many things. One big takeaway was that DML, especially when it's paired with those flexible machine learning methods, really outperformed the more traditional linear methods, especially when those relationships between the confounders and the treatment or outcome were all curvy and nonlinear.
Yeah, that makes sense. That's where DML's flexibility really shines.
Exactly. Another interesting finding was that the main advantage of using those fancy ML methods within DML seemed to be more about dealing with that nonlinear confounding, rather than just being able to handle tons and tons of important confounders. DML can definitely work with lots of variables, but it's not magic. If you have a massive number of really important variables and not a lot of data, even DML can struggle.
What about the strength of the confounding itself? Did that matter?
Huge impact. The stronger the confounding meaning, the more those other factors were influencing both the treatment and the outcome, the more obvious the limitations of the simpler methods became. So if you've got strong confounding, using DML with a flexible ML method that can really capture those complex relationships is super important.
Okay, so strong confounding, you definitely want to bring out the big guns. What about sample size? Does DML need tons of data to work?
Generally, yeah, the more data, the better, especially for those more flexible methods. But even with smaller data sets, they found that DML, even with simpler methods, often still beat the traditional approaches when the confounding was nonlinear.
The paper also looked at different kinds of variables. Ones that were just noise, ones only related to the outcome, ones only related to the treatment. What did they find there?
Well, they found that including variables that were only related to the outcome actually made the DML estimates more precise. But including variables only related to the treatment actually made things less precise and even introduced some bias in smaller samples. They also confirmed that missing important confounders can really mess things up no matter what method you're using. And messing up those controls, like those colliders we talked about, can lead to biased estimates even with DML. So again, thinking carefully about your causal model is really, really important.
No shortcuts there. What about the number of folds you use in that cross-fitting thing? Does that make a difference?
Yeah, it can. They found that for smaller data sets, using more folds up to a point could really help those ML models learn better. And repeating the whole DML process many times with different random splits each time really helped make the estimates more stable and reliable, especially when dealing with those smaller data sets or super complex data.
Okay, so lots of nuances to consider. They also applied DML to a real-world data set, looking at how much air pollution affects housing prices in Boston, right?
Exactly. They were kind of redoing, but with modern tools, this classic study from back in 1978. That original study used something called hedonic price regression, which involved making some pretty specific assumptions about how all the different factors, like the features of the houses, the air pollution levels, and of course, the prices were all related.
So how did the DML results compare to that older study?
One of the first things they noticed was that when they ran DML a bunch of times on the data, especially with those flexible machine learning methods, they got different estimates each time. This showed how sensitive the results could be to how you split the data. So they tried different numbers of repetitions and found that more repetitions led to more stable results, which really backs up their advice about doing those multiple runs.
Makes sense. So what about those actual estimates of the air pollution effect on housing prices?
Well, they found that the simpler methods like basic OLS regression and just using XGBoost by itself without the whole DML framework, they tended to find a bigger negative effect of air pollution. But when they used DML with those more flexible ML methods like GAMs, neural networks, Lasso with some extra flexibility added in, XGBoost within the DML framework, and random forests, they generally found that air pollution had a more negative impact on prices compared to what the original study had found.
Interesting. So the original study might have actually underestimated the effect of air pollution.
That's certainly possible. The authors suggest that those assumptions the original study made about how all those factors were related might have been too restrictive. The fact that the DML approach, which lets the data speak for itself a bit more, pointed toward a bigger negative effect is definitely something to think about. And they also looked at how well each ML method was doing at predicting things in that first stage, which gives us some clues about which of those DML estimates might be the most trustworthy.
Really cool stuff. So after this deep dive into DML, what are the main takeaways for our listeners who are thinking about using this in their own work?
Well, DML is really powerful at dealing with confounding, especially when you suspect those relationships in your data are all curvy and nonlinear. It basically lets you use the power of machine learning to get a much more accurate estimate of that cause and effect relationship. But, and this is a big but, it's still really important to remember that DML is primarily an estimation tool, not a magic solution to every problem. If you have issues with unobserved confounders or you're including those bad controls we talked about, DML won't save you. You still need to understand your data, your field, and those cause and effect relationships.
So when would you say DML is the right tool for the job?
Based on the paper, if you suspect nonlinear confounding and you have a decent amount of data, ideally more data points than important variables, then DML is worth trying out. They also recommend being a bit cautious with using Lasso all by itself, especially if those nonlinearities might be important. Instead, try out those more flexible algorithms like random forests, XGBoost, or neural networks, and make sure you take the time to tune those algorithms to make sure they're predicting as well as possible in that first stage.
Any other practical tips for people who want to try this out?
Definitely try running DML with a few different machine learning algorithms and see if you get consistent results. Look at how well each algorithm predicts in that first stage. That can give you a sense of how much you can trust the final estimate. And think carefully about how many folds you use for cross-fitting, especially if you have a smaller data set. And remember, trying different numbers of repetitions of the whole DML process can help you get those stable and reliable estimates. And most importantly, think critically about what you're including in your analysis. Are there confounders you might have missed? Are you sure you're not controlling for things you shouldn't be? Tools like causal diagrams can be really helpful here. And if you're working with a really small data set, be aware of the limitations of DML and maybe compare your results to those from simpler models. And even if you're pretty confident in your model, DML can be a great way to double check and make sure you're not missing anything.
So DML really gives us a powerful way to explore those causal relationships, especially when things are complex and messy, like in the real world.
Yeah, exactly. It's a way to really embrace that complexity and let the data guide us towards better understanding, as long as we're careful and thoughtful about how we use it.
Well, this has been a truly deep dive into double machine learning. It's given me a lot to think about.
It's a fascinating area with so much potential.
Yeah.
And remember, while DML can handle a lot of the heavy lifting when it comes to dealing with confounding, understanding those underlying causal relationships is still crucial.
Right. So don't just blindly apply it. Think carefully about your research question, your data, and the assumptions you're making.
Exactly. And for all you listeners out there, I hope this has sparked some ideas about how you might be able to use DML in your own work.
It certainly has for me. Now, here's something to ponder as we wrap things up. Could DML, with all this amazing data we're collecting now, could it actually go from being this kind of niche, advanced technique to becoming like a standard tool that everyone uses? And if that happens, what new challenges might pop up? As we rely more and more on data-driven approaches to understanding cause and effect, what do we need to watch out for? That's something to think about.
That is the question, isn't it? The future of causal inference. It's an exciting time to be in this field, that's for sure.
Absolutely. All right, well, that's all the time we have for today's deep dive. Thanks for joining us.
Until next time.